Wait, did you know that astronomy, humanity's oldest science, is facing a crisis so deep it could topple everything we believed about the universe? And I'm not talking about conspiracy theories or science fiction. I'm talking about real data, billion-dollar telescopes, and scientists publicly admitting that something is profoundly wrong. Galaxies that shouldn't exist, numbers that refuse to add up, structures so gigantic they violate the laws of physics. And the more we look at the cosmos, the more it seems to be telling us one thing: your story about me is wrong. Stay until the end, because what I'm about to reveal will completely change the way you see reality. You probably heard about dark matter, dark energy, the Big Bang. These concepts form the foundation of the standard cosmological model, the framework we use to explain literally everything in the universe. But here's what nobody tells you: that framework is crumbling. And not quietly. Telescopes around the world and in space are capturing images that simply don't make sense within what we know. Galaxies too mature appearing too early. Expansion rates of the universe that vary depending on how you measure them. Cosmic structures so massive they should be impossible to exist in the time the universe had to form them. It's as if the cosmos is holding up a mirror to science and saying, you got close, but you still haven't fully understood. And when you truly comprehend what these contradictions mean, what they imply for physics, for cosmology, for our understanding of reality, everything changes. Because this isn't a crisis of failure. It's a crisis of opportunity. A moment very much like when astronomers discovered Neptune by predicting an invisible planet, or when Einstein completely rewrote our understanding of gravity. Every major leap in science begins at the edge of confusion, at the exact moment when the universe stops obeying the rules we expected. Let me show you where everything started falling apart. For over a century, cosmology was anchored by a model that seemed unshakable. The universe began hot and dense, expanded, cooled, formed stars, built galaxies, and eventually evolved into the cosmic web we see today. Countless observations supported this narrative. The cosmic microwave background, the distribution of galaxies, the abundance of chemical elements, the accelerating expansion of space. Every new telescope seemed to reinforce the story. But beneath that confidence, something quieter was brewing. Subtle discrepancies that would later become impossible to ignore. At first, the universe's misbehavior seemed like statistical noise. A galaxy too bright here, a cluster too dense there. Nothing dramatic enough to break the model, but strange enough to provoke long meetings and cautious scientific papers. Then came the deep field images, snapshots of the earliest eras of the cosmos, captured with clarity no one had ever achieved. Suddenly, astronomers were staring at galaxies that shouldn't exist, systems too massive, too structured, too evolved for how young the universe was at that moment. Instead of the expected population of small, chaotic proto-galaxies, the cosmos was showing something far more mature, something that defied everything the timeline said should be possible. As more of these anomalies accumulated, the tension in the data grew. The calculations didn't align with predictions. The story we told about the early universe, its speed, its structure, its evolution, no longer fit what telescopes were revealing. And the more precise the observations became, the more the universe seemed to drift away from the organized framework cosmologists had built. It wasn't a sudden collapse. It was a slow, steady unraveling, a kind of cosmic whisper saying, look again. The moment the James Webb Space Telescope began returning images, the crisis accelerated dramatically. Webb was designed to peer deeper into time than any previous instrument, going back to the first 100 million years after the Big Bang. What astronomers expected to see were small, faint, embryonic galaxies just beginning to form. What they actually saw were gigantic, brilliant systems bursting with stars and heavy elements, structures that should have required billions of years to assemble. It was like discovering skyscrapers in a world where you expected to find tents. And these observations weren't isolated cases. They were everywhere Webb looked. Massive galaxies sitting impossibly close to the dawn of time. Stars that seemed too old for the universe's age at their locations. Chemical signatures that required multiple generations of stellar evolution, even though insufficient time had passed for those generations to occur. The early universe was supposed to be a chaotic fog, dimly lit by the first small, unstable stars. Instead, it was vibrant, organized, shockingly mature. Something was deeply wrong. And this wasn't the only wound in the model. Elsewhere, telescopes measuring the universe's expansion were producing numbers that refused to agree. Local measurements using exploding stars and pulsating variables painted a picture of faster expansion. Meanwhile, measurements tied to the early universe suggested something slower. Both methods were sound. Both experiments were precise. And yet they diverged so drastically that cosmologists had no choice but to confront the possibility that a pillar of their model, the very rate at which the universe expands, might not be understood at all. Meanwhile, vast cosmic structures revealed by radio surveys challenged another fundamental assumption: the idea that the universe looks basically the same in all directions on very large scales. Instead, astronomers found gigantic walls and filaments stretching across space in patterns so vast they bordered on violating the physical limits of what could have formed in the available time. The telescopes weren't failing. They were succeeding so well that they forced a reckoning. They showed us a universe that had outgrown the story we'd written for it. Among all the anomalies shaking modern cosmology, none are as striking or as unsettling as galaxies forming far earlier than they should. These are not faint smudges of light or primitive star clusters. They are vast, luminous, complex systems filled with heavy elements, spinning disks, and stellar populations suggesting long cycles of birth and renewal. And yet, by all our calculations, they appeared at a time when the universe should still have been in its infancy. To understand why this is such a big problem, imagine trying to read a book and finding entire chapters written long before they should have existed. That's what these galaxies represent. According to the Standard Model, the universe needed hundreds of millions of years just to form the first stable stars, and much longer than that to create enough heavy elements to build complex structures. But these early galaxies tell a different story. One where the universe raced through its developmental phases with impossible speed, assembling enormous systems almost as soon as the cosmic lights came on. Some of these galaxies contain elements like carbon, oxygen, and iron in quantities that require multiple generations of supernovae. But those generations require time, far more time than exists between the Big Bang and the moment these galaxies appear. Their masses are staggering, rivaling or surpassing the size of the Milky Way at a point in cosmic history when such behemoths should be unthinkable. Simulations struggle to reproduce them. Models fail. Explanations multiply, each one stretching the boundaries of known physics. Perhaps star formation was far more efficient in the early universe than we believed. Perhaps dark matter clumped more aggressively. Perhaps the laws of gravity behaved differently under extreme conditions. Or perhaps, in the most radical interpretation, our timeline of the early cosmos is simply incomplete. These galaxies shouldn't exist, and yet they do. And because they do, they stand as monuments to a universe that refuses to be confined by our expectations. But wait, because it gets even stranger. If there's one problem in modern cosmology that refuses to go away, it's the conflict over the universe's expansion rate. For decades, astronomers believed they had finally pinned down this elusive number, the Hubble constant, a value describing how fast space itself stretches over time. But as measurements improved, confidence didn't grow. Instead, something far stranger happened. The universe began giving two incompatible answers. One method looks to the nearby cosmos. Observing Cepheids, supernovae, and other reliable standard candles, astronomers calculate how fast galaxies around us are receding. These local measurements consistently point to a faster rate of expansion. Another method reaches deeper into time, studying the cosmic microwave background, the ancient afterglow of the Big Bang. That relic light carries information about the early universe's density, temperature, and structure. From it, cosmologists infer a different expansion rate, slower, more measured, and fundamentally at odds with the local value. These aren't sloppy measurements or outdated techniques. They are the most precise observations ever made, backed by decades of refinement, and yet their conclusions diverge a way that should be statistically impossible. It's as though the universe is offering two narratives of its history, each internally consistent but mutually incompatible. Some scientists argue that new physics may be needed, something that changes the behavior of dark energy or alters the laws of early universe expansion. Others speculate that unknown particles or fields could have influenced cosmic evolution, in ways we've never considered. What's clear is this: the expansion disconnect isn't going away. Every year, new measurements push the tension higher. Every attempt to reconcile the numbers with the standard model only creates more questions. The deeper we look, the more the universe seems to assert that something fundamental in our understanding is missing. This disagreement isn't a crack. It's a geological fault running straight through the foundation of cosmology. And here's what makes all of this even more disturbing. While the expansion crisis was brewing, another mystery emerged from a completely different corner of astronomy. Radio surveys and galaxy mapping missions began revealing structures so enormous they defied the limits of what should be possible within the universe's lifetime. These weren't small quirks or isolated statistical cases. They were colossal formations, superclusters, filaments, and voids spanning billions of light years in size. Patterns stretched across cosmic distances so vast, they seem to violate one of the most cherished assumptions in cosmology: that the universe is homogeneous and uniform on the largest scales. According to the standard model, the cosmic web should only grow to a certain size, constrained by the amount of time gravity has had to pull matter together since the Big Bang. But some of the formations we've observed exceed that threshold by staggering margins. They're too long, too connected, too coherent. They imply that gravity had help, or that it operated under conditions far more efficient than our theories predict. Just as troubling is the distribution of these structures. They appear in orientations and alignments that are difficult to explain as random. Some seem to follow patterns that hint at influences stretching across epochs, as though the early universe carried imprints of processes far more complex than expected. The existence of these superstructures forces cosmologists to confront uncomfortable possibilities. Perhaps dark matter behaves differently on the largest scales. Perhaps the initial conditions of the cosmos weren't as uniform as the standard model assumes. But there's something scientists still can't fully explain, and that's where things get really interesting. One of the great surprises of the modern era of astronomy isn't the universe's chaos, it's its order. For decades, cosmologists believed the early universe was a turbulent place filled with small, irregular clumps of matter that would eventually merge into galaxies. Everything was supposed to be messy, uneven, and primitive, but observations tell a different story. The universe's earliest structures show a level of smoothness and organization that defies the standard model's predictions. Instead of broken fragments slowly assembling into larger systems, many early galaxies appear coherent, stable, and even elegant. Their symmetry, their rotation, and their distribution challenge the idea that the early cosmos was dominated by violent, chaotic processes. It's as if structure emerged with unnatural efficiency, as though the universe had a head start it shouldn't have had. Even more troubling is the uniformity observed across vast regions of space. Temperature measurement from the cosmic microwave background reveal a cosmos that is far more even than should be physically possible given a short time light had to travel across early space. This horizon problem, a cornerstone of the cosmological crisis, suggests that parts of the early universe that should never have interacted somehow ended up sharing an almost identical temperature. Inflation theory was introduced to explain this extraordinary smoothness, proposing a brief moment of exponential expansion in the early universe. But even inflation, once cosmology's hero, is beginning to show signs of strain. As new observations roll in, inflation simplicity gives way to a tangle of competing models and theoretical complications. Some physicists now argue that inflation may not be the full story, or that it may hide deeper mysteries we're still unable to grasp. For decades, dark matter and dark energy were seen as the elegant solutions to astronomy's biggest mysteries. They explained missing mass, explained the universe's accelerated expansion, and tied the standard cosmological model together with mathematical precision. These invisible components made up 95% of the universe. And though invisible, they provided the scaffolding that allowed galaxies to form and space itself to stretch. But as new data pours in, even these once reliable pillars have begun to show cracks. Dark matter, for instance, doesn't always distribute itself as theories predict. In some galaxies, stars move as if dark matter is overwhelmingly dominant. In others, it seems to vanish almost entirely. Certain dwarf galaxies exhibit internal dynamics, so bizarre they appear to challenge the very concept of dark matter halos. And then there are galaxy clusters where dark matter appears offset from visible matter in ways that defy traditional interpretations. These inconsistencies suggest that dark matter may not behave universally, that it may interact, clump, or evolve under conditions we don't yet understand. Dark energy is no less perplexing. It was introduced to explain the observed acceleration of a universe's expansion. But new measurements hint that the acceleration may not be constant. It may vary. It may evolve. It may not fit the simple equation cosmologists once believed it did. If dark energy changes with time, then our entire understanding of cosmic evolution, past, present, and future, may require rewriting. The smooth, predictable picture of expansion becomes a far more dynamic, uncertain phenomenon, one that may be influenced by unknown fields or forces. Worse yet, dark matter and dark energy remain completely undetected in laboratory experiments. Decades of effort have revealed nothing. No particles, no signatures, no interactions beyond gravity. It's as if 95% of the universe is made of something that refuses to reveal itself in any way we can directly measure. And while this doesn't disprove their existence, it reminds us that the concepts we lean on so heavily may be placeholders, temporary frameworks waiting for deeper explanations. Gravity has been the most reliable force in physics since Newton's days. It shapes planets, builds stars, sculpts galaxies, and governs the universe's evolution. Einstein's general relativity refined it into one of science's most beautiful theories. A framework so precise it predicts the bending of starlight, the rippling of space-time, and the choreography of black holes with uncanny accuracy. But as astronomers push gravity to its limits, testing it across cosmic distances, signs are emerging that even this mighty theory may not tell the full story. On galactic scales, stellar motions often defy expectations. The outer edges of galaxies rotate faster than they should, even after accounting for dark matter. Some systems show gravitational behavior that differs drastically from others of similar mass. The delicate structure of galaxy clusters reveals tensions that standard gravity struggles to resolve, and the early universe presents an even deeper challenge. Galaxies appear to have formed and grown more quickly than gravity should allow. These anomalies raise a profound possibility that gravity itself may behave differently on the largest scales. Some physicists propose that general relativity, though exquisitely accurate locally, may require modification when applied to the cosmos. Others suggest that gravity may be emergent, shaped by deeper unknown principles. There are theories where gravity weakens or strengthens depending on the environment's density. Others imagine that space and time themselves are woven from quantum structures that create gravitational effects we haven't yet learned to predict. The idea of modifying gravity isn't new, but what is new is the accumulating evidence that something may indeed be missing, not because Einstein was wrong. Einstein was almost certainly right within the realms he tested, but because the universe is forcing us to extend his ideas into territories he never imagined. Just as Newton's laws weren't discarded but expanded, our understanding of gravity may now stand at the threshold of a similar transformation. Every major scientific revolution begins with a moment when the impossible becomes real. Planets orbiting other stars were once dismissed as fantasy until the first detection shattered centuries of certainty. The universe's expansion was unthinkable until observations forced us to accept it. Black holes were mathematical curiosities until they emerged from theory into reality. Today, astronomy stands at another such moment, one in which phenomena once deemed impossible are appearing with increasing frequency, demanding explanations our current models cannot provide. Some of the earliest galaxies we observe possess masses that rival today's most mature systems, yet they formed only a blink after the Big Bang. Enormous cosmic structures stretch across distances that seem to violate the standard model's maximum allowed size. Stars appear older than the universe should allow at their location in time. Even the cosmic microwave background, long considered the Big Bang's triumph, contains subtle anomalies that don't fit neatly within the accepted framework. One by one, these impossible findings accumulate, not as isolated accidents, but as a pattern that whispers the same truth. The universe may be governed by physics we haven't yet discovered, and while this may seem unsettling, History shows that such moments are the catalyst for progress. Before Neptune was found, Uranus's motions didn't make sense. Before relativity, Mercury's orbit broke the rules. Before quantum mechanics, atoms misbehaved. What we're witnessing today in cosmology is not unprecedented. Science has faced crises before, moments when observations refused to align with accepted theory. In each case, these moments weren't failures, but turning points that reshaped our understanding of the world. When observations repeatedly challenge a model's elegance, it becomes clear that its beauty may be hiding deeper complexity. The universe isn't wrong. Our story is. And that's not discouraging, it's electrifying. Perhaps dark matter isn't a single particle, but a spectrum of unknown phenomena. Perhaps dark energy isn't a constant, but a dynamic field. Or perhaps entire epochs of cosmic history remain undiscovered. We're standing at a frontier, and frontiers are always marked by uncertainty. Astronomy isn't in crisis because it's failing. It's in crisis because it's evolving. New data is forcing growth. The universe is bigger, older, younger, faster, slower, and more surprising than the models we built to describe it. This isn't the end of our understanding. It's the moment right before everything changes. The crisis facing modern astronomy isn't an ending, it's a beginning. It marks the moment when our current understanding has reached its limits. Beyond those limits lies an expanse of new physics waiting to be discovered. Every anomaly, every contradiction, every impossible galaxy is part of that revelation. They're not signs of failure, they're signs of dawn. The dawn of a new cosmic story that will redefine everything we believe about the origin, evolution, and fate of the universe. If this journey into the cosmos blew your mind, imagine what else we'll uncover together. Hit that subscribe button right now, because we're just getting started. Every week, we dive deep into the mysteries that science is only beginning to understand. From quantum paradoxes to cosmic anomalies, from ancient civilizations to future technologies, this channel is your front row seat to the greatest discoveries happening right now. And here's the thing. The algorithm only shows these videos to people who engage. So if you want to be part of this community exploring the edges of human knowledge, subscribe, hit the notification bell, and drop a comment telling me what cosmic mystery you want us to explore next. The universe is revealing its secrets. Don't miss what comes next.